Section: Introduction. In this section, we explored the capabilities of large language models, LLMs, trained on vast amounts of data and parameters. While these models excel in various natural language tasks, they struggle with complex reasoning and planning scenarios. Advanced prompting methods like chain, tree, and graph of thought have shown improvements in reasoning abilities, but fine-tuning LLMs with high-quality supervised data is crucial for better performance. However, this approach is limited by the quality and scope of available data. To address these challenges, the concepts of self-correction and self-learning have been proposed. LLMs typically refine their responses based on past feedback and learn from sampled responses using reward models like PPO or DPO. Yet, it is still uncertain if LLMs can effectively evaluate their own outputs to improve response quality, especially in tasks requiring intricate planning and reasoning. On the other hand, combining advanced search algorithms like Monte Carlo Tree Search, MCTS, with reinforcement learning has enabled models to surpass human performance in complex tasks such as the game of Go. This leads us to consider if integrating MCTS with LLMs could create a new self-improving paradigm. By examining ALPHAGO, we identified three key factors for its success: expert and self-play data, tree search for exploring potential moves, and clear feedback from the game environment. However, integrating MCTS with LLMs poses challenges such as limited high-quality data, search efficiency in vast language spaces, and subjective feedback in natural language tasks. To address these challenges, we introduce ALPHALLM, a framework for LLM self-improvement. ALPHALLM includes an imagination component to generate prompts, ADA MCTS for efficient language task searching, and a trio of critic models for accurate feedback guidance. Experimental results on mathematical reasoning tasks show that ALPHALLM can enhance LLM performance significantly, approaching levels comparable to GPT-4. In summary, our contributions involve addressing challenges in applying ALPHAGO self-learning to LLMs, introducing ALPHALLM for self-improvement, and demonstrating performance enhancements on mathematical tasks. Section Summary. In this section, we explore the challenges faced by large language models, LLMs, in complex reasoning tasks and the limitations of fine-tuning them with supervised data. We introduce ALPHALLM, a framework that combines Monte Carlo Tree Search, MCTS, with LLMs to enable self-improvement without additional annotations. By leveraging ALPHALLM, we demonstrate significant performance enhancements on mathematical reasoning tasks, showcasing the potential of this approach in advancing LLM capabilities. Section: Related work. In this section, we explore the related work on using large language models, LLMs, for effective search strategies and self-improvement. Effective search strategies are crucial for tasks involving complex reasoning and planning, such as games like Go. Various search methods have been studied for reasoning tasks. One approach is beam search with dynamic pruning, where low-quality options are removed. Another method involves maintaining a tree or graph to represent progress in solving a problem, expanding potential solutions iteratively. Our approach, based on the Monte Carlo Tree Search, MCTS, algorithm, differs in defining search steps as tokens or sentences, offering more flexibility. We also focus on leveraging MCTS for self-improvement, carefully designing the search process by combining multiple critique signals to guide it effectively. As a result, our approach outperforms others. Self-improvement for LLMs aims to align them with human preferences and values, using supervision from within the LLM itself. Obtaining reliable critique signals to distinguish good and bad responses is crucial. Previous methods relied on handcrafted rules to filter out low-quality data, while later work proposed general principles for the LLM to evaluate its responses. We suggest using MCTS outputs to further train the LLM for self-improvement, as they offer higher quality responses. Other research explores gathering critique data from question and answer websites or using external tools to enhance the LLM's critique abilities. In our problem formulation, we consider an LLM with a policy that generates responses based on input sequences. The policy operates sequentially, generating tokens based on previous context. This process can be viewed as a Markov decision process, MDP, where states represent the current context, actions are token generation, and rewards evaluate the response quality. By applying reinforcement learning methods, we aim to optimize the policy to maximize rewards. The self-improvement problem involves iteratively refining the LLM policy to enhance performance. This includes learning from synthesized prompts and responses obtained through advanced search algorithms. Challenges include generating suitable prompts, efficiently searching through possible actions, and obtaining precise feedback. Section Summary. Related work. Effective search strategies are crucial for tasks involving complex reasoning, such as Go and planning. Different search methods have been explored, including beam search with dynamic pruning and maintaining a tree or graph to represent progress in solving questions. Our approach, based on the MCTS algorithm, offers flexibility in defining search steps and leverages multiple critique signals to guide the search process effectively, resulting in improved performance. LLM self-improving. Self-improvement for LLM involves aligning it with human preferences using supervision from its internal knowledge. Our proposed method leverages MCTS outputs to train the LLM, enhancing its critique ability for self-improvement. This approach differs from others that rely on heuristic rules or external tools for data filtering and guidance, aiming to improve the LLM's responses based on human preferences. Section: Monte Carlo Tree Search. In this section, we present an overview of Monte Carlo Tree Search, MCTS. MCTS is a method used for optimizing policies in decision-making scenarios. It involves four main phases: selection, expansion, evaluation, and backpropagation. During the selection phase, we recursively choose child nodes from the root node based on the upper confidence bound, UCB, bandit formula. This formula considers factors like visit counts and average node values to balance exploration and exploitation. Next, in the expansion phase, the tree grows according to a defined policy. Then, in the evaluation phase, we estimate the value of the newly added node using sampling or model-based techniques. Finally, in the backpropagation phase, we update the values of ancestor nodes based on the newly added node's estimated value. The architecture of our approach, ALPHALLM, consists of three main components: the imagination component for creating learning examples, the efficient search component called ADA-MCTS for finding high-quality trajectories, and critics to guide the search process effectively. We start with an initial dataset, cal.d, (0) containing prompt response pairs. To enhance this dataset, we generate new prompts, cal.d, (1) by applying a transformation function to examples from cal.d, (0). This process aims to diversify and enrich the training data for the policy model. When applying MCTS to large language models, LLMs, conducting token-level search for each token as an action becomes challenging due to the large vocabulary size. To address this, we introduce option-level MCTS, where each option represents a sequence of tokens. This approach allows for a more comprehensive search beyond a single token or sentence, enhancing flexibility and effectiveness in tasks where subtle variations significantly impact outcomes. Option-level MCTS involves selecting options based on initial states, generating actions using a policy, LLM, and terminating based on a function. This method enables deeper searches, broader coverage of the search space, and reduces the need for frequent feedback requests. By using options instead of individual tokens, we streamline the search process and improve efficiency. Section Summary. In this section, we introduce Monte Carlo Tree Search, MCTS, as a sampling-based algorithm for policy optimization in decision-making problems. MCTS involves four phases: selection, expansion, evaluation, and backpropagation, where nodes are recursively selected based on upper confidence bound, UCB, bandit. New nodes are added, values are estimated, and results are propagated back. Additionally, we propose option-level MCTS for LLMs, where each option represents a sequence of tokens or sentences, enabling a deeper search with reduced complexity compared to token-level or sentence-level searches. Section: Importance-Weighted Expansion. In this section, we discuss the importance-weighted expansion technique. When working with option or sentence-level tree search, it has been common to assume that each node in the tree has the same predefined width or branching factor. However, this fixed width can lead to inefficient search spaces. To address this, we propose dynamically adjusting the branching factor based on the importance of each node. By allocating more resources to important nodes and fewer to less important ones, we can explore more efficiently and not overlook potential solutions. The importance of a node is determined by its value function and the maximum value difference from the current state. Nodes with small value deviations may not need further exploration, while those with significant differences are worth investigating further. The number of children allowed for a node is set proportionally to its importance using a factor alpha. Next, we consider state merge, where similar states under the same node can create redundant subtrees. To increase diversity and cover more ground with limited rollouts, we group similar options together. This grouping strategy helps us explore a wider problem space efficiently. We use heuristic functions to measure similarity between options and decide whether to merge them or create new groups. Moving on to fast rollout with specialized LM, we highlight the importance of simulation in projecting future trajectories for effective MCTS. By simulating various trajectories, MCTS can better estimate the outcomes of different actions. To speed up this process, we introduce a specialized LM as the fast rollout policy for rapid simulations. Lastly, we introduce the critic models in ALPHALLM, including the value function predicting future rewards, process reward models estimating node quality, and outcome reward models assessing overall trajectory quality. These critic models provide essential guidance signals for the search process. Section Summary. In this section, we introduce importance-weighted expansion, a method that dynamically adjusts the branching factor of each node in the tree search based on the importance of the node. By allocating more resources to nodes of higher importance and fewer to less important nodes, we can efficiently explore promising solutions without wasting resources on less significant paths. Additionally, we address the issue of state similarity by using move groups to enhance diversity among states, allowing for more efficient coverage of the problem space during the search process. Section: Value function. In this section, we work on the value function. We use the value function, represented as v_pi s, to predict the expected reward starting from state s_t following policy pi. To train the value function v_pi_phi s with parameter phi, we use the Monte Carlo MC method to estimate the expected reward by averaging rewards observed from many samples starting from state S and following policy pi. The reward from a state is the total of rewards obtained in the future, discounted by a factor gamma at each time step. The MC estimate of v_pi_phi s is calculated as an average of the total discounted rewards from state S in different trajectories. Next, we introduce the policy reward model, PRM, to address the credit assignment problem and improve the learning efficiency of the value function. PRM generates intrinsic rewards to encourage exploring beneficial options, which helps overcome issues of delayed and sparse rewards. PRM predicts the immediate reward that results from taking a specific option in a given state. Instead of using AMLP layer to output a scalar reward, we treat PRM as a text generation task to utilize the model's knowledge for evaluating options. Additionally, we introduce the option reward model, ORM, to guide the Monte Carlo Tree Search, MCTS. ORM evaluates sequences of options to assess how well the entire trajectory aligns with the desired goal. It complements the value function and PRM by providing a comprehensive evaluation of trajectories. ALPHALLM is formulated as a text generation task, similar to PRM, and helps in achieving a balance between exploration and exploitation strategies during the simulation stage of MCTS. Section Summary. In this section, we introduce the concept of the value function, which estimates the expected reward starting from a given state and following a specific policy. We utilize Monte Carlo estimation to train the value function by averaging rewards observed from multiple samplings, considering future rewards discounted by a factor. Additionally, we propose the Process Refined Model, PRM, to address reward sparsity issues by generating intrinsic rewards that encourage exploration of beneficial options, and the Outcome Refinement Model, ORM, to evaluate entire sequences of options for guiding Monte Carlo Tree Search, MCTS, simulations. Section: Policy Self-Improvement. In this section, we have discussed how ADA MCTS can help guide our policy to discover better trajectories. To enhance our policy further, we follow an iterative process with two main steps in each iteration: data generation and policy fine-tuning. In the data generation step, we start with our current policy pi_theta_k and synthetic prompts cal_d_k at the kth round. By running ADA MCTS on cal_d_k, we obtain training data cal_d_k for the policy pi_theta_k. We then select trajectories for each question x_k_i based on the highest critic score in the MCTS forest. Next, we filter out low-quality instances using a quality evaluating function f and a threshold gamma. Moving on to policy fine-tuning, we organize the training data cal_d_k into chat templates between a user and an AI assistant. We then fine-tune the policy pi_theta_k using target loss SFT to update it to pi_theta_k+1. Other training methods like DPO or PPO are left for future exploration. For our experiments, we apply ALPHALLM to mathematical reasoning tasks with clear learning signals. We evaluate our model on datasets like GSM-8K and math, focusing on predicting correct answers and measuring computational efficiency in terms of average rollouts. To assess the performance of ALPHALLM, we compare it against models like GPT-4, GPT-3.5, Claude 2, PaLM 2, and others using COT as our primary prompting method. We also include evaluations with open-source models like Llama 270B and Wizard 70B. Implementation-wise, we use specific policy models for each dataset and incorporate tools like Python SymPy for quality assessment in math. Training details include parameters for MCTS and policy self-improvement, with early stopping based on a devset. Section Summary. In this section, we discuss how to enhance policy through an iterative process involving data generation and policy fine-tuning. We generate training data by running ADA MCTS on synthetic prompts and then filter out low-quality trajectories based on a quality evaluation function. Subsequently, we refine the policy using the obtained data and target loss SFT, resulting in an updated policy for improved performance. Section: Results. In this section, we present the results of our study. We compare the performance of different methods on the GSM-8K and math datasets. Our findings show that ALPHALLM, which uses final answer annotations and improves itself through training on synthetic prompts with responses from ADA MCTS, performs better than Llama 270B and Wizard Math 70B v1.0. Even though these models are trained on a larger set of examples including rationales and final answer annotations, ALPHALLM outperforms them. This highlights the effectiveness and wide applicability of our self-improving framework. When we enhance our model with ADA MCTS decoding strategy, its performance significantly improves, achieving scores of 88.9 and 48.7 on the GSM-8K and math datasets, respectively. After 2 rounds of self-improvement using synthetic prompts, ALPHALLM shows performance similar to GPT-4, indicating a promising approach to enhancing LLM's problem-solving abilities in a self-improving manner with minimal labeled data. We also analyze the performance of different methods with varying numbers of responses, from 10 to 50. Our analysis reveals 2 key findings. 1. Re-ranking using ALPHALLM consistently outperforms self-consistency techniques, showing that ALPHALLM can provide meaningful signals for searching. 2. ALPHALM performs better while requiring fewer rollouts. For example, on the math dataset, ALPHALM achieves better results with only half the number of rollouts compared to re-ranking. This suggests that our efficient MCTS design in ALPHALLM can effectively improve policies, enabling the search for high-quality trajectories with reduced computational cost. We conduct an ablation study to evaluate each component in ALPHALLM. On the GSM-8K dataset, we observe that adding PRM, ALPHALM with fast rollout, and state merging successively improve accuracy, with the best performance achieved by increasing the number of rollouts along with other components. On the math dataset, excluding options leads to decreased performance, highlighting the importance of option formulation in enhancing MCTS flexibility. Additionally, utilizing only intrinsic knowledge for ALPHALM results in a significant drop in accuracy, emphasizing the need for external tools to assess challenging problems effectively. Furthermore, we compare the results of 2 rounds of self-improvement trained on trajectories collected using re-ranking and ADA-MCTS on the GSM-8K dataset. Models trained on trajectories from both methods outperform the initial policy, with ADA-MCTS showing higher efficiency and accuracy. Models trained on ADA-MCTS trajectories, when decoded with ADA-MCTS, perform similarly to GPT-4, demonstrating the effectiveness of ALPHALLM as a self-improving framework. Despite the promising results, there are limitations to address in future work. We aim to explore advanced techniques for generating synthetic prompts, enhance the utilization of MCTS for self-improvement, update critic models continually, and extend the evaluation of ALPHALLM to other domains for broader applicability.